Alrighty. LLMs evolve quickly. Their underlying architecture, not so much. Okay, so I'm going to preface this with I don't know a lot about how LLMs architecture works, like under the hood. I know how to use them in like an API setting. I've set up local LLMs. I've used ChatGPT and Anthropic and all that, and Copilot. I've not actually trained a model, so I this seemed interesting to me. So the decoder only transformer architecture is one of the most fundamental ideas in AI research. Well, for right now. So we'll see. I think ultimately the transformer architecture will not be the one that wins out based on current trajectories. So we'll see what happens. But anyway, new language models get released every day. Gemini 1.5, Gemma, Claude 3, potentially GPT-5 someday. It's been a while, but one component of LLMs that has remained constant over the last few years, the decoder only transformer architecture. Why should we care? Research on LLMs moves fast, shockingly. However, the architecture used by most modern LLMs is pretty similar to that of the original GPT model. We just make the model much larger, modify it slightly, and use a more extensive training and alignment process. For this reason, the decoder only transformer architecture is one of the most fundamental and important ideas in AI research. So, investigating and understanding it deeply is a wise idea. I agree. It's kind of the underpinning of everything right now. For right now, it seems like we've hit a bit of a plateau with transformers. I don't think that we're going to make much more strides. I think we can feed them more data, and I think we can feed them better data and get back something a little bit more useful and maybe a little bit smarter in some sense. But I don't think the things are going to be thinking anytime soon. I don't think they're going to be reasoning about things properly anytime soon. I don't think we're going to reach AGI with the transformer architecture personally. That's just my opinion. I don't think we have the compute for inference. I don't think we have the data. I don't think there's enough data on the internet for these things to consume. So, yeah, I think we're going to need something else. The architecture has 5 components. In the input layer, decoder-only transformers receive a text prompt as input. We use a tokenizer based on algorithm like byte pair encoding to break this text into discrete tokens, words, or subwords. Then we map each of these tokens to a corresponding vector stored in an embedding layer. The process forms a sequence of token vectors that are passed to the model as input. Optionally, we can augment these token vectors with additive positional embeddings. Interesting. So it uses a tokenizer, which is similar to like a programming language. It'll lex the lexer will essentially tokenize all of the different pieces of a programming language or the words essentially. So it's they're using like a lexer for the English language, and then they map them to vectors. And I assume they use vectors because that's what GPUs understand. Like vector math, vector space is what GPUs are great at. That you can process many things in parallel all on a GPU that way. So if you break down this problem into vectors, that makes sense why AI likes GPUs. And then so it's interesting that there's a embedding layer. I didn't realize that there was like embeddings within the AI itself, which is what this seems to be implying. So I find that interesting. That's where the knowledge comes from. I don't know. Causal self-attention is the core of the decoder-only transformer and allows the model to learn from relationships between tokens in the input. The vanilla self-attestation operation transforms each token's representation by taking a weighted combination of the other token representations where weights are given by pairwise attention importance scores between tokens. Causal self-attention follows a similar strategy but computes attention scores for preceding tokens in the sequence. Attention is performed in parallel across several heads, multi-head attention, each of which can focus upon different parts of the input sequence. So it's correlating different tokens together essentially. This is the sort of stuff that like kind of attests to like a sort of advanced autocomplete where it takes the text and understands what's coming next or predicts what's coming next based on the previous tokens. And then because those things are related in the vector space, like those vectors are numbers are similar, you can take those vectors and turn them back into tokens and then generate output. That's my understanding. And so that's what the self attention is, I assume. Feed forward transformations are performed within each block of the decoder only transformer, allowing us to individually transform each token's representation. This feed forward component is a small neural network that is applied in a pointwise manner to each token vector. Given a token vector as input, we pass the vector through a linear projection that increases its size by 4x, apply a non-linear activation function, then perform another linear projection that restores the original size of the token vector. I'm going to be honest with you. Point 3 went completely over my head. If someone out there would like to explain like step 3 in the comments section, I would be extremely grateful. So we can take linear, which is a line in a graph, and then project that out to 4x the size, and a nonlinear the nonlinear activation function. This might be the function approximation essentially that goes on. I'm not sure. The classification head. The decoder only transformer has one final classification head that takes token vectors from the transformer's final output layer as input and outputs a vector with the same size as the vocabulary of the model's tokenizer. Okay. So it's translating it back into the text space using like a reverse tokenizer essentially. This vector can be used to either train the LLM next via next token prediction or generate text at inference time via sampling strategies like nucleus sampling and beam search. Transformer blocks form the body of the decoder only transformer architecture. The exact layout of the decoder only transformer block may change depending upon the implementation, but two primary sublayers are always present: causal self-attention and feed-forward transformation. All right. Self-attention makes sense. Feed-forward transformation, not so much. Additionally, these sublayers are surrounded by a layer normalization module, either before or after the sublayer or both, as well as residual connection. Interesting. So let's go look at this here. So we've got the tokenizer, which makes sense. Causal self-attention, taking the dot product of a bunch of vectors, essentially. So you've got input matrices, and then you turn them into query, key, and value. That's interesting. So it's interesting. So cool is a query, R is a key, LLM isn't one of these things. That's interesting. Output res connection. So there's a looping structure here. And then it goes into these are neural nets, essentially. A bunch of neural nets. Token classification. And then the transformer block. Interesting. Most of this is going over my head. And then that's it. All right. I'm going to say that this is probably a bunch of very good information, but I would have liked to see a little more breakdown of what these individual things are and how they work together a little bit better. This is a little short. This is a little concise for me to grok what's going on, especially this feed forward transformation section. This seems to be black magic to me. So I get the vector space and like computing vectors and correlating them together. That correlates different concepts, different words together, essentially. And then the LLM can be like, oh, if they say this, there's this whole pool of other things that's all related to. And then you can take that and use that for the computation. So that I get. And that's how vector databases work. Essentially, you can output vectors, use vector databases with LLMs to do embeddings, and then you can use those to search the vector database and then figure out things that are related to what you asked and add that to the context window and all that fun stuff. So I would have liked a little bit more from this, but I thought it was all right. It's written by Cameron R. Wolf, PhD. So very smart dude. So yeah, awesome. If you liked this article, if you liked the video, please subscribe and like the video. If you have some more information, like if you want to explain to me how feed forward transformation works or anything else that I got wrong here, add a comment down below. Help me and anyone else who's watching the video out. All right, I think that's it. Have a good one.